So here's a two-way table where researchers randomly assigned 72 chronic users of cocaine into three groups. One group who received desipramine, which is an antidepressant, one who received lithium, which is the standard treatment for cocaine, and a group that got the placebo. And here's the results of the study. So you had 24 people in each group, and they determined whether they relapsed or didn't relapse. So, marginal probability is going to be the probability of one of these categories. So, what is the probability that a patient relapsed? Well, 48 people relapsed out of a total of 72. So your probability is going to be 48 out of 72, which reduces to 2/3. What is the probability that a patient received the antidepressant desipramine and relapsed? So, how many people both received desipramine and relapsed? 10 out of 72. So, both of those are things that we know how to do. We may not have had the words for them, but we know how to find the marginal probability and find the joint probability. The conditional probability of an outcome of interest A given B, condition B, is calculated as this. So this is Bayes' formula, or Bayes' rule. All right, so we read this as the probability of A given B is the probability of A and B over the probability of B. All right, so the probability of relapse, given that they took desipramine, is the probability of relapsing and taking desipramine over just the probability of taking desipramine. Right? So the probability of relapse and desipramine, right, was 10 over 72. And the probability of just taking desipramine, we had 24 over 72. And when you divide your fractions, you keep change flip, and your 72s cancel, and this is 10 out of 24. Another way that we can think about this when we're using a two-way table, two-way tables are so helpful for conditional probability. Like, you always want to be using a two-way table for conditional probability if you can, right? So the given condition is desipramine, so we're only looking at the people who take desipramine. I have no idea if I'm saying that correctly, by the way. I don't really care. But we can ignore all of this because the given condition is taking the antidepressant. So we're only looking at the people that relapsed out of the people who took desipramine. So the given condition is going to be our total. So instead of our total being out of 72, the overall total, now our total for our probability is the total number in the given condition, the people who took desipramine. Okay? If we know the patient received the antidepressant, desipramine, what's the probability that they relapsed? So here, what we want is, so the probability of relapse given desipramine. We just calculated that. We can also do the probability of relapse given that they received lithium, right? So this would be So the probability of relapse given lithium would be probability of relapse and lithium over just the probability of getting lithium, right? And so that is 18 out of 24. And then the probability of relapse given the placebo, we're just looking at the relapse and the placebo category. So, what conclusion can you draw from the fact that all of these probabilities are different? We can infer that the treatment, desipramine, lithium, or the placebo, affects the probability of relapse. They are dependent. We can also go the other way. If the relapse is the given, what's the probability that they receive the desipramine? So now our total is the 48 who relapsed. 10 of those receive the desipramine. And we could do the same thing for lithium and the placebo as well. Right? So we can use the conditional probability to check for independence. If A and B are independent, then the probability of A given B is equal to the probability of A. Right? The probability of a coin landing heads on the second throw, given the probability that it landed heads on the first throw, is just the probability of landing heads on the second throw. It's just 1/2, because they're independent. But that inference also goes the other way. If probability of A given B is equal to just the probability of A, then they're independent. So if they're independent, this is true, but if this is true, then they're independent. Going back to that example of the poll where they asked people whether they think owning guns helps protect citizens, right? Overall, 0.58% of the population, 58%, said that owning guns protect citizens, right? So that's your A, would be protect citizens. Given that the resident is white, is 0.67, given that the resident was black was 0.28, and given they're Hispanic is 0.64. So the probability of A given B of protect citizens given white does not equal the probability of just protect citizens. Right? And same for black and Hispanic. Therefore, race and saying that gun ownership protects citizens are not independent because the probabilities are not the same. Now, within a margin of error, but they are most likely dependent. And in later units, we will figure out, we will be able to determine mathematically how big is a large enough margin of error, how much variation is enough to say whether they're actually dependent or whether it's just due to random chance. So, if conditional probabilities calculated on sample data suggest dependence between two variables, the next thing we would do would be conduct a hypothesis test. And so that's going to help us determine whether the differences that we saw are likely to have happened by chance or whether there is something else going on. If the difference between the conditional probabilities is large, there's a stronger evidence the difference is real. If you have a large sample, then even a small difference can provide strong evidence. Of a real difference. Right? So Under which condition would you be more convinced of a real difference between the proportions of whites and Hispanics who think widespread gun ownership protects citizens? A sample of 500 or a sample of 50,000? 50,000, right? If we have a large sample size, then this difference of 3 percentage points is unlikely to happen by chance. If we have a sample of 500, then it's possible that a difference of, 15 people could be could go one way or the other. And so that's the law of large numbers. Earlier, we saw that if two events are independent, their joint probability is the product of their probabilities. If the events are not independent, the joint probability is calculated slightly differently. Right? So, if A and B represent two outcomes or events, then the probability of A intersection B is the probability of A times the probability of B given A. If A and B are independent, then the probability of B given A is just equal to the probability of B. If A and B are independent. So, just like our addition rule, this is one of those rules where part of the formula simplifies in certain cases, in this case, in the case of independent events, right? So before, it was the probability of A intersection B is the probability of A times the probability of B, because that's the same as the probability of B given A if the events are independent. If they're dependent, we have to calculate this conditional probability, probably using the formula a couple slides ago. Note, it should also work the other way, right? Probability should also be the probability of B times A given B, right? Which, if they're independent, would be just the probability of A. Multiplication is commutative. We should be able to do it either direction. Generically, if the probability of A given B equals probability of A, then the events A and B are said to be independent. So, if they're independent, then this is true. If this is true, then they are independent. The inference goes both ways. So what that means is that knowing condition B doesn't tell us anything about the probability of A. Mathematically, if we know that A and B are independent, then we get this, right? So using that conditional probability formula, probability of A given B is probability of A and B over the probability of B, and the probability of B's cancel out. Don't worry about it, you're not going to have to prove this formula. So, American Cancer Society estimates that about 1.7% of women have breast cancer. The Susan G. Komen for the Cure Foundation states that mammography correctly identifies about 78% of women who truly have breast cancer. An article published in 2003 suggests that up to 10% of all mammograms result in false positives for patients who do not have cancer. These percentages are approximate. Welcome to the fun world of statistics where nothing is ever certain. And in later units, we get to put numbers on just how uncertain we are, which is going to be a fun time. But we'll pretend like these numbers, like we have confidence in these numbers. So, when a patient goes through the breast cancer screening, there are two competing claims. Either the patient has cancer or the patient doesn't have cancer. If a mammogram yields a positive result, what is the probability that the patient actually has cancer? So, what we're looking for is the probability of cancer given that we get a positive mammogram. right? So 2 competing claims. So we can do this doing a tree diagram, and the tree diagrams are super helpful for this type of conditional probability. So either the patient has cancer or they don't have cancer, and we go ahead and put their probabilities. 1.7% chance of cancer means a 98.3% chance of no cancer. Those are pretty good odds. I'd be pretty happy with those odds. Now, the probability of a positive or negative result depends on whether the patient has cancer or not. So if the patient has cancer, there's a 78% chance of a positive result, which means a 22% chance of a false negative. If the patient doesn't have cancer, there's a 10% chance of a false positive, which means a 90% chance of a negative. And if we multiply down the branches of the tree diagram, we get the probabilities of cancer and a positive test, cancer and a negative test, no cancer and a positive test, and no cancer and a negative test. Now, how does this help us, right? We want the conditional probability of having cancer given a positive test. And if we use that conditional probability formula, that's the probability of cancer and a positive test over just the probability of having a positive test. Cancer and a positive test is 0.0133. Just a positive test is that 0.0133 plus this 0.0983 false positives here. So the probability of that positive test is the sum of the 2 ways that you can get a positive test, if you have cancer or if you don't. And if you put that into your calculator, that's a probability of 0.12. So even if you get a positive test, that's a 0.12 probability, a 12% probability that you actually have cancer. So maybe get a second opinion. So this is one of my favorite things about probability. Honestly, no joke, I am being totally serious right now. I love when you get an unexpected result from doing something with probability. And so this is actually a thing that I think about a lot, particularly when, I go and get a test for strep or something. And apparently strep tests are only 70% positive. And at that point, I'm like, well, why even bother knowing what I do about inverting probability and conditional probabilities? Because the chance of having strep is so much smaller than the chance of not having strep. And so with only a 70% accuracy, you're going to have way more false positives than you're going to have actual true positives, which means that your chance of actually having strep, given that you test positive for it, is pretty low. And your chance of not having strep, given you test negative, also pretty low. So, in conclusion, strep tests are useless. Go tell that to your doctor next time you have a sore throat. Suppose a woman who gets tested once and obtains a positive result wants to get tested again. In the second test, what should we assume to be the probability of this specific woman having cancer? It's what we just calculated. It's 0.12. Right? Her probability of having cancer, given her positive test, is 0.12. So we're going to use that as the basis for our second tree diagram. What's the probability that she has cancer if the second mammogram also gives us a positive result? Right? So now use 0.12 as her probability of cancer and 0.88 as the probability of no cancer. Still have the same probabilities of positive and negative, given cancer and no cancer. And so we multiply down the branches of the tree, and get probabilities here. So the probability of cancer given 2 positives, right, is going to be the probability of cancer and 2 positives over just the probability of 2 positives, right? Or we can do the probability of cancer and positive using the cancer and no cancer probabilities that we calculated from doing it the first time. So what it ends up being is that 0.12, the 0.12 times the 0.78 gives us the probability of cancer and that second positive as 0.0936. And then we add that to the probability of 2 false positives, which would be the 0.088. And when we divide that, that's a larger percentage, right? 0.52, it's a bigger probability. But that's why we don't start chemotherapy without lots of testing. And you could do it for 3 and 4 and blah, blah, blah. So, this is a special case of Bayes' theorem, which is applicable even when events have more than just 2 outcomes. So, this is the long version of Bayes' theorem. The probability of outcome A given outcome B is going to be the probability of B given A times the probability of A over all the ways that B, that we can have probability B, basically. So, we can do this even when we have more than just 2 outcomes. It just means basically that you add more things in the denominator. So, here we only added 2 things in the denominator. But if you had more options, then maybe you would have more ways to get a positive result besides just cancer or no cancer. You would just add all of them in the denominator. A common epidemiological model for the spread of diseases is the SIR model, where the population is partitioned into 3 groups: susceptible, infected, and recovered. This is a reasonable model for diseases like chickenpox, where a single infection usually provides immunity to subsequent infections. Sometimes these diseases can also be difficult to detect. So, all of this talk about diseases is particularly relevant right now. But this would not necessarily be a good model for COVID-19 because a single infection of COVID does not necessarily provide immunity to subsequent infections. There are people who have gotten COVID more than once, which, sucks. Imagine a population in the midst of an epidemic. I wonder what that would be like, where 60% of the population is considered susceptible, 10% is infected, and 30% is recovered. The only test for the disease is accurate 95% of the time for susceptible individuals, 99% for infected individuals, and 65% for recovered individuals. So, accurate meaning returning a negative result for susceptible and recovered, and a positive result for infected. So, here we've got multiple options. So draw a probability tree to reflect the information above. And we want to know if they've tested positive, what's the probability they're actually infected. So, susceptible, infected, and recovered. 60% susceptible, 10% infected, 30% recovered. So, 95% reliable. The test is 95% reliable for susceptible individuals. Susceptible individuals are not infected, so 95% of the time they get a negative result, 5% of the time they get a positive result. 99% for infected, So 99% they get a positive, 1% they get a negative, and 65% for recovered. So 65% of the time they get the negative, 35% they get the positive. And we multiply down the branches of the tree, and that's going to give us all of the different probabilities, the joint probabilities. Probability of being susceptible and getting positive, susceptible and getting negative, etc. Remember, those are the joint probabilities. Right? So the probability of being infected given a positive result is going to be the probability of being infected and having a positive result. Maybe I should make that an intersection symbol just so that we get used to using that. Right? Over the probability of getting a positive result. And so this probability of getting a positive result is going to be the sum of all three ways that we can get a positive. So, our probability of being infected and getting the positive result is this 0.099. Our probability of just getting the positive result is the 0.099 plus the 0.03 plus the 0.105. And you put that in your calculator and you get 0.4233. Remember, when you're putting this in your calculator, to put parentheses around the denominator. And that's conditional probability. We're going to have so much fun with conditional probability. I've got loads more examples, but not in this video.